Theoretical recap. ICMP, Internet Control Message Protocol, is a network layer protocol, OSI Layer 3, used primarily for diagnostic and error reporting purposes. Unlike TCP or UDP, ICMP does not carry application data. It carries control messages. The most familiar use of ICMP is the ping command, which sends an ICMP echo request to a target host and waits for an ICMP echo reply. This round-trip exchange lets you verify reachability and measure latency. An ICMP packet is encapsulated inside an IP packet. The IP header contains source and destination addresses, TTL, time to live, and the protocol number 1, reserved for ICMP. The ICMP header itself contains a type field, for example, type 8 equals echo request, type 0 equals echo reply, a code field, usually 0 for ping, a checksum, an identifier, and a sequence number. The payload is typically a small block of padding bytes. A common beginner mistake is confusing ICMP with a transport protocol. ICMP has no port numbers and does not establish connections. Another frequent error is ignoring the TTL field, which is crucial in network security and traceroute logic. Keep in mind that firewalls often block ICMP, so a lack of reply does not always mean the host is down. Mini example. Running ping 8.8.8.8 sends ICMP type 8 packets to Google's DNS server. Capturing this with Wireshark reveals the full packet structure in real time. This is exactly what you will do in this workshop. Workshop brief. This workshop puts into direct practice the concepts covered in the previous chapters on network vocabulary, hosts, links, packets, and IP addressing. You already know what a packet is and how IP addressing works. Now you will go one level deeper. You will generate real network traffic using ping, capture it live with Wireshark, and dissect an ICMP packet layer by layer. This is a foundational skill for any cybersecurity or DevSecOps professional, since understanding low-level traffic is a prerequisite for threat detection, intrusion analysis, and penetration testing with tools like Nmap or Wireshark. Your recommended time allocation for this workshop is 3 hours. You must submit your deliverable before the deadline expires. Manage your time accordingly. Installation and setup should take no more than 30 minutes, packet capture and analysis around 1 hour, and writing your report approximately 1 hour. Setup and environment. Before starting, ensure you have the following tools installed and functional on your machine. Windows, Mac OS, or Linux are all acceptable. Wireshark, free, open source packet analyzer, download at wireshark.org, a terminal or command prompt with access to the ping command. Administrator or sudo privileges, required to capture packets at the network interface level. If you are working in a restricted corporate environment or virtual machine, verify that your network adapter is accessible by Wireshark. If you encounter permission issues on Linux, you may need to run Wireshark with sudo or add your user to the Wireshark group. On Windows, install nppat during the Wireshark setup process. It is the capture driver that makes packet sniffing possible. Once Wireshark is running, identify the correct network interface, the one that has active traffic, usually your Wi-Fi or Ethernet adapter. Do not start capturing yet. Capture and analysis steps. Begin by opening a terminal. Choose a public target that responds to ICMP, for example, 8.8.8.8 Google DNS, or 1.1.1.1, Cloudflare DNS. Before running ping, set up a capture filter in Wireshark to isolate ICMP traffic only. Hint, the display filter ICMP will help you focus. Start the Wireshark capture on your active interface, then immediately run the following command in your terminal. On Linux/Mac OS, ping c48.8.8.8. On Windows, ping n48.8.8.8. This sends exactly 4 ICMP echo request packets. Stop the capture once the ping command completes. You should now see a series of ICMP packets in Wireshark. Select one ICMP echo request packet and expand all layers in the packet detail pane, bottom left panel in Wireshark. Your task is to identify and document the following fields with their exact values from your capture. 1. Ethernet frame, source MAC address, destination MAC address, ether type. 2. IP header, source IP, destination IP, TTL, protocol field value. 3. ICMP header, type, code, checksum, identifier, sequence number. 4. ICMP payload, length and content, hex or ASCII. Then select the corresponding ICMP echo reply and perform the same analysis. Compare the two packets, what changed and what stayed the same. Pay particular attention to the type field and the TTL value in the IP header. Think about what the TTL value in the reply tells you about the path taken. Deliverable and submission. You must produce a short written report, minimum 400 words, maximum 800 words, in PDF or Markdown format. Your report must include a screenshot of your Wireshark capture showing at least one echo request and one echo reply, with the packet detail pane expanded. A structured table or list documenting all the fields requested above for both packets. A written analysis section, at least 150 words, in which you explain in your own words what each field means, why the TTL matters, and what a cybersecurity analyst could infer from this ICMP exchange. Think about reconnaissance, host discovery, and what information is exposed. A brief reflection, 3 to 5 sentences, on what surprised you or what you found difficult during this exercise. You are allowed, and encouraged, to consult the previous theoretical chapters of this course, Wireshark's official documentation, RFC 792, the ICMP specification, and any other internet resources. You may work alone or ask for help from a peer, but the written analysis and reflection must be your own. Do not simply copy-paste field descriptions from the internet. The goal is to demonstrate that you can read and interpret a real packet capture, not recite definitions. Analytical depth and clarity of explanation will be the primary evaluation criteria.